All right, so in this segment, we're going to continue to talk about electrochemistry, and we're going to make it more quantitative. And to do this, we actually have to figure out how to calculate the electromotive force coming from from the chemical energy in the cell. So in this next segment, the main lecture objective is going to be to compute cell potentials from the cell half potentials. Now these are tabulated and so I'll explain how to do that. So the standard reduction potential, when you're looking at potential energy differences, like the energy you get from some sort of gravitational potential energy, it only depends on the difference. And unlike in gravitation, it's a little hard to tell exactly what, there's no absolute chemical energy. But we can set a reference, same as we set and when we're calculating standard state free energies or enthalpies. And so we can't measure the absolute tendency of a half reaction. Reactions only occur with the other halves of the reaction. You can't have half a reaction, you have to have a whole reaction. So we select as a standard half reaction the reduction of H plus to H2 under standard conditions, i.e. 1 mole of 1 molar H plus, very acidic, and H2 plus at 1 atmosphere. And we arbitrarily assign a potential difference of 0 volts. And it doesn't really matter if it's 0 volts because we're always going to be comparing this reaction to any other reaction. So, this is a reaction that happens in solution with the hydrogen reacting to produce a gas. We have an inert anode like platinum that does not react to the acid. And so this reaction, the potential of this interaction we set to 0. Again, this sort of reaction can only happen in conjunction with another reaction. So it's really, it's an arbitrary convention of which one we decide, because it would decide in a completely different way. And we'd still, when we look at it would cancel. But it allows us to just tabulate everything as one number as opposed to pairing all the differences. So this is the standard hydrogen electrode where you have H plus being reduced to H2 with 1 molar H plus and 1 atmosphere H2. So the reaction, it's just that reduction reaction. So generally we tabulate reduction potentials rather than oxidations. Of course, you can flip around and you get the exact opposite potential for the oxidation, but generally they're tabulated as reduction potentials. So this is the reduction reaction. So how do we measure the electrode potential? Well, we set up an electrode where the oxidation that is occurring, or the oxidation that is occurring, or we do with reaction as well. The point is we've got one cell where reactions occurring, and the other one we're using a standard hydrogen electrode. Of course, we can use a non-standard hydrogen electrode. We could have our H plus at something other than 1 molar, and we'll learn in a couple lecture segments how we can make those corrections. But in this case, we are just looking at the potential energy difference from that. So let's assume it's at standard. So we can measure the potential energy difference. And since we've set 1 as the standard, 1 being 0, then we could attribute the rest of the potential energy of the electrons flowing downhill to be assigned to that, to the anode in this case. And if you have something that's more likely to oxidize than H plus is to reduce, then of course it's going to be positive. You'll get electrons flowing that way. You'll get the reduction of H plus. If you have something that's less likely to reduce, then you'll get it going the other way, and you'd actually get H plus going to H2 going to H plus. Okay, so the standard hydrogen electrode reduction potential is divided to be 0, so we can compare to a particular reduction half reaction relative to that reduction of H plus to H2 under standard conditions. And of course, you could do this same experiment with other electrodes as well if you've benchmarked the first electrode to the standard hydrogen electrode. So there's a lot of different ways you can measure it. You don't always have to measure with the standard hydrogen electrode, but you have to measure at least one compared to the standard hydrogen electrode, so then you can make all the other comparisons. Okay, so the half cell potentials, half reactions with a stronger tendency towards reduction than the standard hydrogen electrode have a positive value for the cell potential of reduction. standard potential of reduction. Half reactions with a stronger tendency towards oxidation than the standard hydrogen electrode have a negative value for the standard potential of reduction. And so for oxidation half reaction, just flip it around. The standard potential for oxidation is just minus the standard potential for reduction. And so this is the important key for the standard potential for a cell. It's going to be the E final, where the electrons end up, minus the E initial, where the electrons start from. Usually when we see differences, it's always final minus initial, that's the convention. And so where do the electrons end up in? They end at the cathode, where reduction is taking place. And they start in the anode, where electrons are being lost from the chemical system into the electrical system. So it's E final minus E initial, E cathode minus E anode, and E reduction minus E oxidation. And so E cell is positive for spontaneous reactions and negative for non-spontaneous reactions. So this is the opposite of delta G, right? Delta G negative means spontaneous. Delta E cell is positive for spontaneous reactions, negative for non-spontaneous reactions. A way to think about this is that if it's a spontaneous reaction, you can get potential energy out of it. So that's a way to think about it. Aha, I can get energy out. My E cell is positive if it's a spontaneous reaction. And if it's a negative reaction, it's non-spontaneous, I get no energy out of that. I have to put energy in for that to happen. Okay, so for the cell potential, a half reaction with a strong tendency to occur has a positive half cell reaction. When two half cells are connected, the electrons will flow, so the half reaction with a stronger tendency will occur, right? If you have one reaction that really wants to happen, one that kind of wants to happen, then it will push towards the one that really wants to happen. So for example, in this case, we have the potential energy increasing from positive to negative. Electrons stuck on a negative electrode are not very happy. They want to go to the positive electrode. So a negative value is a higher potential energy. So because the reduction potential from zinc to zinc 2 plus is negative, then the electrons want to get away from that. They want to get away from the negative and move to the positive. So they'll spontaneously move from zinc to, from the zinc, creating Zn2 plus, to the cathode, where they can move, they can join with H plus to produce H2. So in this case, the zinc is oxidizing because it has a negative potential with respect to the cathode, which has a zero potential. And so overall, then zinc to zinc 2 plus, plus 2 electrons has a potential of plus 0.76. And so if we look at this particular cell, E final is 0. E initial, the reduction potential of the zinc is minus 0.76. So we get a positive 0.76. Electrons will spontaneously move from the zinc anode to the cathode, at which the reduction of hydrogen is taking place.